Okay, today we are going to have the lecture on Linux processes, which is part of module 2 dealing with operating system. Now, a Linux system is operated by the kernel, and the kernel has to manage several processes in the user space. Now, the way it manages those is by keeping some metadata about each of those processes. So it understands what's going on with this process, what does the process want, what is the process consuming, so that whenever the kernel is shuffling the processes to be executed, it has full context about those processes. So for this purpose, the Linux kernel keeps a process descriptor, which is nothing but information about a process. What kind of information does the Linux kernel need about processes? Well, to start with, there is an identifier. It's a PID. PID stands for process identifier. The state is needed, the CPU is needed, the priority of the process is needed. What CPU sets did the process choose to operate on? What virtual memory have we given the process to run on? How much of the process is actually in the resident memory? C groups created. The kernel keeps a bunch of accounting, CPU accounting, IO accounting about the process. Relationships of the process to other processes, parent IDs, child IDs, thread groups IDs, runtime of the process, user space runtime, the system runtime, signal handlers, open files by the process, and many, many more. All of this data set is managed in the process descriptor. Now, the process descriptor is a C structure, and you can go and get the details in the file I've written here in sketch.h, and it is the task underscore struct structure. So all the details are in this process descriptor, and for every process that the kernel is going to run, it will create one such descriptor. So that's how an individual process looks. How do processes come in place? Now, processes are part of a process hierarchy. When the system starts up, there is a process with process ID 0, PID 0. Now, the PID 0 process creates two child processes, the PID1 process and the PID2 process. The PID1 process is the init process for user space processes, and systemd is the popular init process used right now. So the system daemon is going to spawn child processes and manage all of user space processes. So it is the bootstrap process. If you are running an SSH daemon, if you are running a Perl job, Python, a Java process, anything in the user space, it will be a child of PID1. The kernel also has several processes that it runs to manage the kernel space. They are all child processes of PID2, and PID2 is the kernel thread daemon. It is managing all the kernel processes underneath that, like the kworker, ksoftirq daemon, and they manage all the kernel processes. Now, every process has a PID number in the system. That is a unique identifier to the process descriptor. Every process will have a parent process. Processes can have child processes, and by virtue of that, they can also have siblings. Now, the PID in itself is a number between 0 and 32,768. And in a setting, it can be changed, but that's usually the default. And the PID number is recycled. So you'll go to the end, and after you reach 32,767, you know that a lot of the processes before that have been reaped. So it'll start again at the beginning. Now, let us see a true output, sample output. Now, PS is a command that is available in Linux, and it has several options you can use, and I'm using the -E uppercase F option. It gives a few fields more, about processes. So I just ran that, and there's a long output for all processes here. These are the first few that I have put on the screen. You can tell that PID 1 is the first one in that line, and its parent process ID is 0. PID 2 is the second one, and the parent process ID for PID 2 is also 0. PID 1, if you see the right side under command, is systemd. And PID 2, if you go to the right side of that line and see the command, it is kthread d, so the kernel thread daemon. There are a bunch of processes listed underneath it. You can see that for all of those processes, the PPID, the parent process ID, is 2. And that also means that they are all kernel processes. The parent is the kthread daemon. And then you can see all the names on the right side for the commands for these processes. The ksoftIRQ, migration, which handles migration between CPUs, RCU, BH, watchdog, and they go by /0/1, and the slashes indicate the CPU. So when you have a watchdog for every CPU, you'll have one for /0/1/2/3, depending on the number of cores you're running. So by the time I see my Linux kernel boot up, I see 100 processes running just like that. And a lot of those are just by the kernel used for managing processes, and several processes in the user space. So now let us go and see how do processes come to creation and see an example. The kernel creates processes using a system call that is available to user processes. Fork, as a system call, creates processes. Now, the system call is definition is up there, PID_t, fork void. It takes no parameter, and it gives you back a process ID, the process ID of the new process that has been created. Now here's a simple program, sample program, PID equals fork. Now after that we get the self PID of this process using get PID and the parent PID, and then I just write the PID of this process and the parent PID. And I just wanted to see what happens. So on the right side, I see that the completing process statement, printf, that I have after the fork is written 2 times. So what happens in a fork? Why did the print statement write 2 times? Now what fork does is it will create a second process, and will give the second process's PID back as a return value. The second process inherits most of the values from the first process, including the code that is supposed to be run and the next instruction to be run. So now you have 2 processes at the point in fork in that line, and the line after that will now be executed by both of these processes, because the second process that was forked, which is a child process, took most of the memory and default from the first process. That is why the lines after fork are executed 2 times. One by the original process, parent process, and one by the child process that got forked. How can you tell who is which one? So there are system calls get PID and get ppid for parent PID, and I just use those 2 to print the PIDs. So in the first line, the completing process's PID is 13571, the parent PID is 11840. The second one, the PID is 13572, and the parent PID is 13571. Now the parent PID of 13571 is the PID of the first process. You can see that 13571 is the PID of the first process. So that is how you can see that the child process is the second one and the first one is the parent process. And that's how they got created, and they are interrelated. Now this is fun, but when you create another one, maybe you want another process, maybe you want to run a different program. How could you do that? There is a system called execve, and it takes parameters. You give it a path name for the program. The argument values, the first argument for a program is the program name itself. You can pass it the environment variables. And so let's try it here. And we have a program main, and we passed some argument list for date. Now what I'm going to do in that line exec v is, and this is the C library call, is I want to run the date program. And the path for the date program is /user/bin/date. And after that line, I also have a please print me line. Now you can see on the right side when I execute this program that the date is printed. So what happened is the exec v changed the program to run the date program. The please print me line that is after that is never printed. That is because the code segment has been changed by this exec v. It is not going to run the original code segment anymore. It moved to a different program, and that is the date program. And once the date program is completed, this program ends. So now we saw in the first case, we could fork and start a new process. In the second case, we could see how we can actually change the program we are running. Let us have a little bit more fun and try to combine these together. So here I do a fork, and then we do an exec in there as well. And this had been interesting for me to learn as well, just to see who's the child process, who's the parent process, how do they behave with each other. So I've done a print before the fork to see which is the original process. Then we do a PID equals fork. And then if the PID is not equal to 0 versus the PID is equal to 0, we run two different statements. And what you find here is that after the fork, again, you'll have two processes. Only one of them will have a PID not equal to 0. And that is the parent one. The child process at that time will start with PID equals 0. It does not copy over the local variables of the parent. And you could see on the right side, in the print statements, the first print statement is obviously of the parent process. PID is 23,465. And then the next print statement when PID is not equal to 0 is again from the same PID process, 23,465. And in the else statement, I put a little sleep just to separate these two printouts a little. And then I did a print from the child process. And I can see that later on when the print happens, the PID is 23,466. And that is the child process, except that the parent PID for that child process shows as 1. So this was interesting. And the reason it shows the parent PID as 1 and not as the actual parent PID is because the parent process, it doesn't execute off the date command and then it just exits. Once the parent process has exited, the child process is left orphaned. And so part of the systemd PID1 process's responsibilities are to pick up orphan processes and to clear them out. And therefore, the parent process of the child process became PID1, which was systemd took over the orphan child process here. So this is also an example of how the systemd process is relevant and how all processes are managed through the systemd process and how the whole hierarchy of processes is created. Now, these simple instructions of fork and exec actually run programs and they create processes in the Linux space. Good. So we learned a few cool things about the operating system, the basic architecture. We learned about how system calls are made, and we learned about how processes are created and how you can create a process and exec programs. The next module will be on scheduling. Now you can go and get the course catalog links for the other programs and the code in the GitHub URL that I have listed here. And you can try these on your own. You can make modifications and play around with them. That is the best way to learn. And subscribe to the YouTube channel for the